We are in chapter 4 where we are discussing bending. This is the 35th session overall. So this is the penultimate session on bending. Here we discuss curved beams. This again is a glimpse of the overall roadmap covered in the first 4 chapters. This is the last session on the treatment of beams. In the final session, we'll summarize the whole discussion. We are dealing with curved beam here. The analysis of curved beam is similar to the analysis of straight beams. Thus, first we find strain, then stress, and then use the formula summation Fx is equal to 0 and summation Mz is equal to 0. With a straight beam, the beam became curved after moment was applied. This is a curved beam. We haven't applied any moment to it. With the application of moment, the curved beam will get more curved or less curved. There are 3 noticeable differences between curved beams and straight beams. With curved beams, the centroidal axis and the neutral axis do not coincide. Also, with curved beams, variation of stress is not linear. The variation of stress is given by a different formula compared to straight beams. Here, this curved beam has been subjected to a positive moment. The top fiber EP has become smaller. The bottom fiber CD has become larger. So, as in the case of a straight beam, there must be a neutral layer at which the length does not change. Here we have considered EF as the neutral axis. We need to note that as in the case of a straight beam, with a curved beam, loading is considered to be on the axis of symmetry. Since with the neutral axis, the length does not change after application of the moment, r theta here will be equal to r dash theta dash, where the second case is after application of the moment. Consider here that theta has increased by del theta. Then r theta is equal to r dash theta dash can be written in this form. Let us now consider strain of a fiber that is at a distance y from the neutral axis. Initially, the fiber was GH, but after application of the moment, the fiber has become G dash H dash. Initially, the length of the fiber was small r into theta. After application of the moment, the length of the fiber has become small r dash into theta dash. So the change in length is r dash theta dash minus r theta. Now small r dash is capital R dash minus y, which is written here. And small r here is capital R minus y, which is written here. We expand and get r dash theta dash and r theta among the terms, but r dash theta dash is equal to r theta. Cancelling, we get the change in length as minus y delta theta. Strain is given as change in length by the original length. So we took a fiber and the change in length was minus y del theta, and the original length of the fiber is r into theta. So we get strain by this expression. Now y can be written as r, that is capital R minus r, and small r can be written as capital R minus y. So strain can be given in three different forms. Multiplying the strain by the Young's modulus, we get stress, which again is given in three different forms. Now consider this expression. Theta here is the curvature of the original beam, and E is the Young's modulus, so they are constant. Del theta depends upon m, and for a given case, they are also constant. So stress depends upon y and r minus y. The variation of stress is not linear. We'll now look at the distance of the neutral axis and the centroidal axis. Earlier we found out the position of the neutral axis using summation fx is equal to 0. Here, if we consider a section, then there's no horizontal force. So integration sigma x dA is 0. Substituting the first expression of sigma x in this equation, we get this expression. Now here again, E, theta and delta theta cannot be 0. So we get integration capital R minus R divided by R into dA is equal to 0. Therefore, the radius of the neutral axis of the unloaded beam is given by this formula. Now let us look at the centroidal axis. If we have a base axis, then the centroidal distance is given by the right hand side of this equation, where r is the distance from the base axis. We consider that base axis is through the center of curvature. Then we get the radius of curvature of the centroidal axis by this formula. So here in this diagram, we have given the radius of curvature of the centroidal axis denoted by RC, and the radius of curvature of the neutral axis denoted by R. The difference is designated as E. We now discuss flexural stresses in curved beams. As with straight beams, this is done by using the equilibrium equation summation mz is equal to 0. Let us take a section here, then the portion on the left of the section of the curved beam is in equilibrium. Stresses at the section create an internal moment. We get the equation integration minus y sigma x dA is equal to m. This equation is the same as that for a straight beam. We have earlier found sigma x was given by three different relations. Here we substitute the first relation. Also, y is equal to capital R minus small r. Substituting y, we get this expression. The portion E delta theta divided by theta has been taken out of the integration sign. We'll deal with the portion within the integration sign and outside the integration sign differently. First, we look at the portion within the integration sign. Expanding the square, we get this form. Now, the equation with which we gave the radius of the neutral axis can be written in this form. Also, the equation of the radius of centroidal axis can be written in this form. We substitute this relation in the first expression within the bracket and this relation in the third expression within the bracket. Then the portion within the integration sign reduces to RC minus R in bracket multiplied by A. The portion within this bracket has therefore been given in a much compact form. We earlier mentioned that we'll deal with the portion outside the bracket differently. So now we will deal with the portion E delta theta by theta. Consider the third expression of sigma x. Using this expression, we can write E delta theta by theta in terms of sigma x. So here we have substituted E delta theta by theta by minus R sigma x divided by y, and we get this expression. So we have related sigma x to the moment. We earlier designated RC minus capital R as E. We substitute and we then get sigma x is equal to minus my divided by AER. Y can be also written as capital R minus small r. The stress variation for a curved beam subjected to a moment is not linear. The pattern is hyperbolic. We can find the radius of curvature of the neutral axis after load has been applied. The length of the neutral axis does not change. So we earlier found r theta is equal to r dash theta dash. Here we have written theta dash as theta plus del theta. We have expressed this equation in terms of ratios here. We then divide both sides by theta. We have therefore obtained 1 divided by r dash in terms of 1 divided by r. This relation is in terms of delta theta by theta. Now, using this relation, we can find delta theta, or we can give delta theta by theta in terms of the moment. So delta theta by theta is equal to m divided by a into Young's modulus into E. Substituting, we get this expression. So given we know the moment applied and R, we can find out R dash. We have a curved beam to which a moment has been applied as shown. We are given the radius of curvature of the inner surface and the dimensions of the rectangular section. We are required to find out the stress at the inner surface and the outer surface for a section such as AA. We are also given the Young's modulus and asked to find the radius of curvature of the neutral axis after loading. We earlier found out that the position of the neutral axis is given by this expression. For a rectangular section, A is B into H and EA is BPR, which corresponds to the shaded area shown. We integrate from R1 to R2, which is the radius of curvature of the inner surface, to the radius of curvature of the outer surface. The integration in the denominator gives ln r with the limit shown. So we obtain r, the radius of the neutral axis. By inspection, we can obtain rc, which is r1 plus half the height. E is rc minus r. Earlier we found that the stress can be given by this expression. If the moment increases the curvature, then the moment is considered positive. So it is positive here. So we get a negative stress at the inner surface. At the outer surface, capital R minus R2 is negative, and we get a positive stress. The radius of curvature after application of the moment is given by R dash, and we can use this formula. All the parameters are known, and we find R dash. The variation of stress is nonlinear, and you can see that the tensile stress is on the upper portion, which we can physically judge from here as well, the way the moment has been applied. Here we have a curved beam of a rectangular section to which the forces P has been applied. We are not given the force P, we are given the maximum allowable stress. We are required to find out the maximum P that can be applied. We take a cross section at AA, which would have the maximum moment. We consider equilibrium of the portion left of AA. With the force P acting here, there must be a force P acting towards the right of the section. These two forces create a couple, so there must be a moment for equilibrium acting on the section. We'll now find out this distance t, which we need to get the magnitude of the moment. The centroid of the section is at a distance AC from the center of curvature. This angle is 50 degrees. So BC here is AC cos 50. BE is the same as AC. Now subtracting BC from CE, we get the distance D and therefore the moment. We are given the radius of curvature of the centroidal axis and also the height of the rectangular beam. So we can find R1 and R2. For this problem, the radius of curvature of the neutral axis can be given by this expression. BH is the area of the rectangular portion and BA is given by BER, is shown here in the shaded portion. We integrate from R1 to R2. So we have obtained capital R. E is equal to RC minus capital R is given here. We can now find the stresses in terms of P. Axial stress is P divided by the area. The stress on the outer surface is given by this expression. Here the moment is applied so as to reduce the curvature, so the moment is negative. We get the stress in the outer surface in terms of P. And the stress is compressive. This is the stress due to bending, which we add up with the axial stress to give the net stress at the outer surface. This is the expression for stress in the inner surface due to bending. Taking moment as negative, we get the stress in the inner surface as tensile. We then get the net stress at the inner surface. And it is given in terms of P, which we equate to the allowable stress to get the value of P. That can be applied. Here we have a curved I-beam to which a moment is applied as shown. The radius of curvature of the inner surface is given. I-beam is not symmetrical and the distance of the centroidal axis from a baseline such as BP has to be determined. So we determine YC using the usual procedure. YC plus the radius of curvature of the inner surface gives RC. The radius of curvature of the neutral axis for an I-beam is given by this expression. Since B is not constant, in the denominator we use a summation. A here is the area of the I section. For the first expression in the denominator, we use the width of the lower flange. Integrate and then use the limits as shown. For the second term, we use the width of the web. We integrate and use the limits as shown. For the third term, we use the width of the top flange and integrate and use the limits as shown. So we have obtained capital R. E is RC minus R, and we obtain the value for E. We next find the stresses using this expression. Here the moment reduces the curvature and as such is negative. We have obtained the stress in the inner surface and the outer surface. You see that the stress in the outer surface is compressive. If we look at the diagram, then we see that our physical understanding matches with what we have determined for the stresses. We have a semicircular portion with two straight portions here. The cross-section is circular and as such different from the other problems we have dealt with. We are required to find the maximum stress in the inner and the outer surface, and the loading is shown. The maximum moment will occur at a section AA since it is the furthest from the load. We consider equilibrium of the mid portion after taking the section at A. Since there's a vertical load acting here, there must be a vertical load acting at the section A. These two loads create a moment. So for equilibrium, there must be an equal and opposite moment acting on the section A. The radius of the circular section is given, so we can find out the area. We also know the load, and from this distance, we can find out the moment. The radius of curvature of the inner surface of the semicircle is given, and we know the diameter of the circular section, so we can find out R1 and R2, from which we can get RC. For a circular section, the radius of the neutral axis is given by this expression. C here is the radius of the circular section. So we find out capital R. We also find out E, which is RC minus R. We then find the stresses. The stress due to the axial load is P divided by A, which we have obtained here. The stress due to moment is given by this expression. Here the moment is trying to reduce the curvature, so the moment is negative. The stress due to bending in the inner surface is coincide, and we add the stress of the axial load to get the net stress on the inner surface. The stress in the outer surface is compressive. Again, we add this to the tensile stress due to the axial load to get the net stress. Here we have a curved beam of a triangular section which is fixed at one end and to which a load is applied at the other end. Inner surface is the arc of a circle, and the outer edge is also the arc of a circle. The distance YC is one-third of the height, where yc is the distance from the base to the centroid of the section. So RC is the sum of the radius of this inner arc plus yc and is given as shown. R1 is the radius of the inner arc and R2 the radius of the outer arc. We consider a section near where the beam is fixed. Since such a section will be subjected to the maximum moment. Taking such a section and considering the equilibrium of the whole beam, we can see from equilibrium of forces that there must be a vertical force acting upward. Now, considering equilibrium of moment of this section, we see that the forces create a moment, and as such, there must be a moment that would act on the section to neutralize the moment created by the forces. We can find out the forces or the stresses due to the axial load, where we know the axial force and divide it by the area. The axial stress is compressive. To find the stress due to the moment, we first find R, which is the radius of curvature of the neutral axis. For a triangle, R is given by this formula. Substituting R1 and R2, we get the value of R. E is given as RC minus capital R, and we can obtain E. We now find the stresses on the inner surface of the curved beam. So we have substituted R1 for R, both in the numerator and denominator. Capital R minus R1 is positive here. The stresses due to the moment on the inner surface is negative. So stress on the inner surface, both due to the axial load and due to the moment, are negative, and they are summed up to get the net stress on the inner surface. Similarly, we found the stress on the outer surface. We substitute R2 in the equation, and here capital R minus R2 is negative. The stress on the outer surface we get is positive due to the moment. The stress due to the axial load was negative, so the net stress on the outer surface is lesser than the stress due to the moment only.